In this video, we are going to work on problem 4.1.3 from the textbook. Consider the function f defined on R by the following formula. F of x is x squared if x is greater than or equal to 0, and f of x is 0 if x is less than 0. And here is the graph of the function. When x is less than 0, f of x is 0. And when x is greater than or equal to 0, f of x is just the squaring function. And in the first part of the problem, we have to prove that f is differentiable and find the derivative of the function at all x in R. And in the second part, we have to determine whether the derivative function is continuous and whether the derivative function is differentiable. Now we are ready to work on the first part of the problem. So we're gonna fix any x bar in R. And we will consider three different cases. Case 1, x bar is greater than 0. In this case, we consider the following limit. The limit of f of x minus f of x bar over x minus x bar as x approaches x bar. Okay? And over here, x bar is greater than 0, so f of x bar is just x bar squared. So this is equal to the limit of f of x minus x bar squared over x minus x bar as x approaches x bar. Okay? So this is 0. And this is x bar. Okay. And because x bar is greater than 0, and x approaches x bar, then x is greater than 0 when it is sufficiently close to x bar. So this limit is equal to the limit as x approaches x bar of x squared minus x bar squared over x minus x bar. And as you can see, this is just the derivative of the squaring function at x bar, and therefore we can easily see that this is 2 times x bar. Okay. So you can see that the limit of f of x over minus f of x bar over x minus x bar as x approaches x bar is 2 times x bar. Therefore, f is differentiable at x bar, and the derivative of the function at x bar is 2 times x bar. Now we consider the second case where x bar is less than 0. Again, we consider the limit of f of x minus f of x bar over x minus x bar as x approaches x bar. And in this case, because x bar is less than 0, f of x bar is equal to 0. So we are going to replace f of x bar by 0. So this is the limit of f of x minus 0. So I just write f of x over x minus x bar as x approaches x bar. Okay? And remember that x bar here is less than 0. So when x is sufficiently close to x bar, x is less than 0. So f of x is also 0. So in this case, this is the limit of 0 over x minus x bar as x approaches x bar. And this is just 0. So in this case, f is also differentiable at x bar, and the derivative of the function f at x bar is equal to 0. Now we consider the third case where x bar is equal to 0, and again we consider the limit of f of x minus f of x bar over x minus x bar as x approaches x bar. Okay. So because x bar is equal to 0, f of x bar is equal to 0, and here we replace x bar by 0 as well. So this is just the limit of f of x over x as x approaches 0. Okay. But as you know, f of x is x squared if x is greater than or equal to 0, and 0 if x is less than 0. So at this point, we don't know what formula for f of x we should use. So we are going to look at the left limit at x bar and the right limit at x bar. So at first, we will look at the right limit at x bar. And in this situation, x approaches 0 from the right. So x is strictly greater than 0. Therefore, f of x is equal to x squared. So we replace f of x by x squared in this case. And see that this is just the limit of x as x approaches 0 from the right, and this is 0. Okay? And also, we will look at the left limit at x bar. Of f of x minus f of x bar over x minus x bar. And as you can see, this is just the left limit of f of x over x at 0. Okay. Now, here x approaches 0 from the left. So x is strictly less than 0, and so f of x is equal to 0. Then this limit is equal to the limit of 0 over x, and x approaches 0 from the left, and this is just 0. Okay. So we have seen that the limit of f of x minus f of x bar over x minus x bar as x approaches x bar from the right and from the left are both 0. So the limit of f of x minus f of x bar over x minus x bar as x approaches x bar is equal to 0 in this case. Therefore, f is differentiable at 0. And the derivative of the function at 0 is equal to 0. So to summarize, we have the following derivative formula. F prime of x is equal to 2x if x is greater than 0. And note that when x is equal to 0, the derivative is 0, so we can combine it to this case. So we have that f prime of x is 2x if x is greater than or equal to 0, and 0 if x is less than 0. Now we are going to work on the second part of the problem. We will determine whether the derivative function is continuous and whether the derivative function is differentiable. Recall that f prime of x is 2x if x is greater than or equal to 0, and 0 if x is less than 0. And this is the graph of the derivative function. Again, it is 0 if x is less than 0, and 2x if x is greater than or equal to 0. Based on the formula of the derivative function, we can easily show that f prime is continuous at any point in R. Okay, so now we are going to show that the derivative function is not differentiable at 0, and therefore it is not differentiable. Okay, so to do so, we will look at the limit of f prime of x minus f prime of 0 over x minus 0 as x approaches 0 from the right and the left. So at first, we look at this limit as x approaches 0 from the right. So over here, you know that x is greater than 0. So f prime of x is equal to 2x. And as you can see, f prime of 0 from the formula over there, f prime of 0 is equal to 0. And you can easily see that this limit is equal to 2. Okay? And the limit of f prime of x minus f prime of 0 over x minus 0 as x approaches 0 from the left is equal to the limit of this is 0 minus 0 over x as x approaches 0 from the left. Again, over here, because x is strictly less than 0, f prime of x is 0. So here I replace f prime of x by 0 and f prime of 0 by 0. It is easily, we can easily see that this limit is 0. So you see that the left limit of f prime of x minus f prime of 0 over x minus 0 is different from the left limit. Therefore, the limit, this limit, as x approaches 0, does not exist. And so, f prime is not differentiable at 0. Okay, so we have completed solving